Hello. Alright, and just check that everything is properly set up. Yeah, here we go. Cool. I'm actually sharing what I was working on just before this thing, which is doing a bunch of preparation work for the Terraform provider for Incus. So we're looking at doing a 1.0 release. As part of that, we can now went through things with some of the other contributors to that repo, to specifically Fabian yesterday, to look at kind of the gaps between what we have in Incus and what the provider supports, and just trying to kind of fill in those gaps before a 1.0 release. At which point we want to have like a proper stable API and only do additions from that point on. So just before this live stream, I was kind of going through my notes and finding a bunch of issues, and I've actually now shared a link to that as well on Mastodon and Twitter, so that if anyone's got some spare time and wants to help out, there's a bunch of things here that people can do to get Terraform to really support everything that we do in Incus. But this is not the topic of this live stream. The topic of this live stream is instead this repo, which got actually published just a few minutes ago. And that's effectively the very initial structure of Incus OS. So gonna go maybe a bit of background as to what Incus OS is. I did mention it in previous live streams as something that that we were looking at to try and really round up kind of all of the different angles as to how to use Incus. So when you're thinking of Incus and you know running it on a system, there are three main ways that we really want to offer and support. And like those new initiatives are not going to replace any of the others. The most common way today is you pick your distro of choice, you go and install the Incus package, either directly from the distro or from a third-party repository, and you run that. And that's the most common. That's what a lot of people do on their laptops and the like, and this works just fine. Now, when you try to scale that up, that's where it can get a bit more annoying. Like when you're dealing with larger lab environments or small production clusters or the like, if you've got to go and manually install Incus and keep it up to date and configure everything correctly, especially if you start mixing in things like Ceph and Oven and those kind of more complex systems, it gets tricky. And that's where the other thing we announced and have been maintaining for a while now, called Incus Deploy, makes sense. Incus Deploy effectively uses a mix of Terraform and Ansible to deploy your cluster and then deploy all of the needed packages on top of that, do all of the configuration, clustering, and initialization for you. So that's been working really well, but it still very much relies on having an initial OS installation on those machines that you also need to keep up to date and configure properly on your side. The good thing is that most of it is done through Ansible, so it's easy to go and mix that up with what you already have managing those systems. And now we go on to the third piece, which is Incus OS. So the goal behind that one is to have a extremely safe, extremely lightweight, fully encompassing environment that can be installed directly on a machine, booted up, and is up and running. You don't need to care about what a Linux distro is. You don't need to care about how to, update packages, configure things, and you're out. It's much more of an appliance type environment where you just put it on a USB stick, plug it in, boot the machine, you're done. That obviously comes with a bunch of kind of trade-offs and like some of those being very positive, especially for production environments. Some that will probably be annoying to more advanced power users who will probably prefer to just install Incus as a package on their own distro. So some of the main benefits of this approach is going to be safety. So the way this stuff is built is that it's fully immutable, fully signed. So this starts up with what's called a unified kernel image. So it's effectively a very large EFI binary, which includes the kernel itself, the init RAM disk, as well as the kernel command line boot parameters. This big file is then signed And that signing key is what you should then load as in your secure boot trust store on those machines. So you could actually go as far as completely wiping the secure boot trust store, so removing the Microsoft keys and all that stuff, then loading just that key in, at which point the only thing that the machine can boot, provided there's no firmware bugs, will be that particular unified kernel image. And then the unified kernel image itself contains in its boot parameters, so still part of what's signed, includes the root hash for dmverity tree. dmverity, for those not familiar with that, you probably have already used it, you just don't know. This is what's used, amongst other things, on Android devices. I think they've migrated to fsverity these days. But effectively, what it does is it's a way to fully sign a disk image and validate that signature as it's being read, rather than having to do it up front. So basically, you boot the machine, secure boot is configured, can only boot the unified kernel image. The unified kernel image has the root hash of the dmverity tree. The kernel boots initRD loads. It's gonna go and look at the GPT partition table, find the root disk. Not really a root disk actually. That's gonna be another thing to talk about with partitioning, but find the OS disk, let's call it that way. It will find that disk, and then it will find the associated verity partition, so the validation partition. It's gonna go and check that the root hash lines up with what it was told it should be, and then tells the kernel, okay, I want a block, like a device mapper device to be set up, which uses this data partition and this verity partition. And from that point on, any reads that are done through that device mapper device will get validated. And if anything was modified, whether intentionally by someone trying to attack the system or because of random corruption, it's going to fail the read. It's never going to let you actually read untrusted, invalid data effectively. So at that point, the system has that read-only OS image that it can read, and it can boot from that. Then you go into the partitioning phase, where if it's a first boot, and almost like pretty much all of that stuff is done through systemd and systemd related tools effectively. So there is a systemd, don't remember the name, but systemd partitioner effectively, which looks at the repartitioning files and goes ahead and then creates the needed partitions. So you will already have had the OS partition and verity partition, but then it's gonna go and create a partition for persistent data. And that partition is gonna get encrypted. Now that actually gets us into the other aspect of security. So far we went through secure boot, dmverity. The other thing that's actually done in parallel to that is TPM attestation of everything. So it's expected that the system has a TPM. Currently, I've not done any tests without it. We'll probably make it work without it, but that's going to require entering a passphrase on boot, that kind of stuff. But with the TPM, what happens is the firmware is measured, the kernel, so the UKI, that big image, gets measured, and pretty much anything else that we want to throw at the TPM can get measured. That effectively, all of that goes into some different registers within the TPM, and we can then have the TPM lock effectively a key based on the system being in a known state. So having the registers be in a particular state. And the key it's gonna hold is the encryption key for the persistent storage. So what that means is, so long as you're booting an expected image on the system that didn't have its firmware modified, and you've not corrupted anything on disk, the PCR states, so the register states within the TPM, are gonna be at the expected value, which is then gonna allow us to automatically unlock the encrypted storage. And that way it's completely transparent. You don't even know that things are encrypted effectively, and the machine can be rebooted without needing any kind of manual assistance. So there's a question about whether TPM is going to be needed. I've not tested it without it. We want to support booting without a TPM. But as mentioned, what's going to happen then is we still want the data to be encrypted. So it won't be able to automatically decrypt it. So you will effectively have to provide a passphrase on boot. You might be able to reconfigure this to not be a passphrase, but be like a USB stick you need to have connected in or something like that. But effectively, the TPM allows us to do passwordless, promptless decryption of the data. If there's no TPM, then we can't do that. So then you need to be prompted for a passphrase to decrypt the storage on boot. And for anyone kind of wondering, like if that sounds familiar, it's because it's a pretty common way of doing it. I mean, this is how BitLocker works. This is how most of the TPM-based encryption stuff works. And that's why if you've dealt with Windows and BitLocker, if you go and modify some system files, it's gonna break the state and require the recovery key to be entered, as people have noticed with the cool CrowdStrike thing not too long ago. And same thing if you update your firmware. I think on most Windows systems they actually tell you if you're going to be updating your firmware, you should turn off BitLocker, then update the firmware, then turn it back on, specifically to avoid getting into that state where the TPM no longer lines up and you have to enter your recovery key. And if you don't know your recovery key, then you're done. There's no way for you to access the data. So this is effectively the security aspects of how that whole stuff works. The system itself is effectively read-only, so you can't start and install packages. It's going to be extremely, extremely restrictive because we don't want to make it like we want this to effectively be a lockdown appliance. Like you should still be like, obviously you can go and modify the files and rebuild the image for yourself if you want, but once it's on a system, we don't want it to. We want it to be like a proper appliance. You don't really think about it, just works. That can be updated in a very safe way because nothing can possibly have changed. So to that goal, one thing we're actually doing is we don't provide the shell at all. So I'll show you in a bit what the image currently looks like. It doesn't do too much like with what I've published on GitHub. Like I've got more things that are still in flux on my side. But with what I've got on GitHub, the image boots, but you don't get a login prompt. There is no users, there is no shell, there's no SSH, there's no way for you to really get in. There's actually one way to get in, which is during development, if you run that image on Incus, so if you run it within an Incus VM, then it does run the Incus agent, which lets you actually get a shell in. I mean, that's how I'm doing the development and testing and all that stuff. But then for production, we will be removing that. The other aspect of this that's not been implemented yet, that I've been doing a bunch of reading and testing, but I've not actually pushed yet on GitHub, is the update system. So again, like all of that stuff is kind of based on your systemd OS image concept. So that's what the OSI, all of those OSI files are about. And for the update system, the way that works is you actually double the number of partitions, except for data. Data would be shared, but you double the OS and Verity partitions effectively. And then it works as an AB type boot. So there's a tool that takes a new image, writes it to disk in the other set of partitions from the ones that are currently in use, and then changes the EFI boot order to boot the new UKI that points to that other set of partitions. Then you reboot the system and you're on the other set. The interesting thing there is that I believe they're using the next boot option within EFI, or they're using systemd boot. I don't remember. But effectively, the concept is that you can do it as a one-time thing. So boot on the new image. If it never reaches some state during boot, then it's effectively considered to be bad. And if you reboot the machine, it's going to reboot on the previous image. So that allows for safer updates effectively, where if something goes wrong, well, worst case scenario, you just restart the machine and you're done. that's the pretty common way that it's done, like for any kind of production hardware usually. I mean, like if you look at like enterprise grade switches, it often works that way. Servers reasonably often have double EEPROM for the firmware as well, which works effectively the same way. It's the pretty safe pattern of if you're starting to deploy this on dozens, hundreds, whatever of servers, or if you're running that, like say you just want to have a small Incus deployment at each of your branch offices, if you're running like a corporate type environment, you don't really want to risk an update just breaking everything, and you don't want to have to send people. So that's where having that AB mechanism where you can just have someone bounce the power and you're done becomes quite useful. So that's going to be sysupdate, which is the other systemd component to specifically manage the AB system with the updates. And the other thing we should probably talk about is what's in what's in the image currently. So currently, ironically, and that's why I didn't want to republish this until now, it doesn't actually have Incus in it yet. And that's for a pretty good reason. We don't actually want Incus itself to be in the image. And that might sound a bit weird, but bear with me, it actually makes sense. So if you're running a cluster and you want to do updates, if you want to update the OS image, it's pretty straightforward. You evacuate the server in that cluster, and once it's empty, you apply you just reboot to get a new update. That's fine. But now, if you've ever run a cluster, you probably know, or if you've seen one of our previous live streams on the topic, if there is a database change, every single server must update at the same time. And that's where things get problematic if Incus is tied to the OS image itself, because it would then now require you to empty an entire cluster just to reboot all of the servers to then restore things. But now at that point, you've literally taken down everything you're running on the cluster, which kind of defeats the purpose. So that's why we want to run Incus separately from, have it stored separately from the base OS image, so that we can update Incus to a new version separately from having to reboot the machines. And the way this is done is yet another systemd thing, which is sysext, so system extensions, which allows you to effectively put a layer on top of the base OS. So we'll have the base OS, which is in this case based on Debian testing, with all of the core packages for things like Oven, all the file systems, ZFS, all that kind of stuff. And then we'll have that system extension, which includes what you would normally see in /opt incus if you're using my packages on Ubuntu or Debian. So effectively, Incus and the very tightly tied components that comes with it will be in that system extension. And that means we can now go and update the system extension and rotate it to newer versions separately from the OS. So if we are dealing with both there being an OS image update and a major Incus update, we can decide which one we will do first. We could do a rolling update on all of the servers one by one for the OS and not touch Incus at all. And then once we're done, update the Incus image on all of them at the same time, which then just restarts the control plane for 30 seconds and you're back online. Or you can do it the other way around with first doing the update for the Incus side. Once you're on the new version everywhere, then you can start doing a rolling reboot of the servers for the OS side. So yeah, that's kind of the idea behind this. There's more that needs to be added still. Other things I've been kind of working on that's not quite ready to publish yet, but what we have here, even if we include the sysext layer, which is not in the repo right now, you would get an image that boots that starts Incus. Okay, that's good. But that's not very useful because you don't have a way to get a shell. You don't have a way to actually talk to that Incus deployment. So that's where there are a few more pieces that needs to come in. The first piece is going to be some basic out-of-the-box experience / initial provisioning. It will probably be done initially, at least, by just having a file on disk, which is read on first boot that includes, hey, this is the network config you need to apply. And then as soon as we're on the network, then we can have Incus respond and you can interact with it and you can bring up the rest from there. That also still doesn't get you too much control, because what happens if you want to reboot that machine? You don't have a shell. You don't have any way to do that. So that's where another component comes in that we've been working on, which will be actually probably like Incus OS daemon or whatever we're going to end up calling it. It's a daemon that sits on all of those servers that handles effectively like a few tasks for us. Like it's got its own API, and through it we can get some information about the OS itself, about available updates. We can run debug and support type commands to get information out of the system and see kind of what's going on in case of an issue. And it's also it's like the current plan is, and I'm still kind of debating whether that's a good idea or not, but we'll say, is to chain that from the Incus API so that you still have a single entry point, which is like talking to the Incus API, and kind of like with the UI, effectively having a /OS endpoint in the API, which lets you talk to that local daemon for the OS sides of things. And that way, through the API, you can now query any server within the cluster. You can check what version it's running, what are the pending updates, trigger those pending updates. You can check on the status of things like Oven and Ceph, if Ceph is in use or Oven is in use. You can do some more of those system-wide, like OS-wide management tasks that way, including doing a reboot. And within a cluster, a reboot will be properly tied into Incus, which means it will do an evacuation for you and a restore for you. So you can effectively say, I just want to apply this OS update. And if you say do it now, it will download, evacuate everything, reboot the machine, comes back up, restores the instances for you, and you're done. So this will make things quite a lot easier to manage. The other thing this daemon needs to manage for us is going to be installation. So, and again, we'll see that in a few minutes when I show you the current image, but currently there's no installer. So you end up with a disk image that if you can dump directly onto your OS drive and boot, then it works. It will just resize itself and it's fine. A lot of people are gonna want, especially in home lab environments, are gonna want to have this on a USB stick they can plug in and then install. So the current thought I've got there is simply to have that daemon also handle that for us. So you would plug the USB stick, you would boot, it will still act as if it's fully installing on the USB stick. So it will create the partitions, encryption, all that kind of stuff on the USB stick for you. And it would be perfectly functional as it is. So you do have a working Incus you can work with, but everything is just on that USB stick. And then through the API, you would tell the OS daemon, hey, I actually want to install onto this disk instead. And it will just copy itself over there and then reboot the machine. At which point you don't need the USB stick anymore. The OS has been moved to the actual drive. So the idea there is really like to limit the amount of tasks that are needed like on the system itself. It's really, you should be able to basically put a small YAML file like on top of the image you download from us that just says this is the network configuration we expect. Plug that into the system, boot it, and then it will listen on the network on that address, and you can go and talk to it, and you can then do everything else from there. Like you can create your storage pools, you can create your cluster, you can do all of the updates, you can do all of that stuff directly through the Incus command line from another system. So yeah, that's basically the idea behind this, and a bunch of that has been going on for months now, in like different stages of completion. So I just did like an initial dump of the pieces that I've moved the least onto GitHub, so I can kind of go through those changes with you now, and then we'll have more coming. I also need to open a bunch of issues so we can just track kind of the pieces that still need to fit in. And I think if we got a bit of time in this live stream, but already been talking for half an hour, so we'll see. I might try and add some more pieces in there. Like we'll see in the demo, it's still a bit rough. Like it currently that shows a massive wall of text on boot, which most people don't care about too much. But we could still tidy that stuff up with like a splash screen type stuff with Plymouth. I currently don't have any of the file system tools installed in there, so one of the things I would like to add is putting ZFS in there, kind of following the same pattern I've got for other things in that image, and just gonna show how it's possible to change the image, rebuild it, test it, and then take things from there. Just before doing that, I see that there's been a question around whether Incus is going to support Bcachefs. Probably. So we do have a open issue on that on the Incus repo, so a feature request. And I believe we had someone do a bit of looking at the tools and kind of how that fits. It shouldn't be a very, very difficult piece of work to do, but it's also not really been a priority for the core Incus team at this point. So it's one of those where, like, if you really care about it, maybe give it a shot. Either you know, trying to contribute a storage driver directly if you're comfortable with writing some Go code. A lot of it is really copy paste from whether it's BFS or ZFS, like taking one of the similar storage drivers and copy paste that one and then change all the commands effectively to try and line things up. Or if not, it might still be useful to provide effectively for everything, like provide in the issue for every single action that we need to do, provide the commands that are needed to do it through the Bcachefs tools. Because with that, then it's pretty easy for us to start filling in an initial backend without having to do too much research ourselves on this. All right, so let's just go through the commits first, and there are just 5, no way of kind of clean things up, and then we'll just do a demo of where that thing stands right now. So let's start from oldest. So initial commit is very boring. There's literally no code in there. It's just our normal boilerplate code of conduct, contributing guideline, and the licensing file. So this is as usual on the release under Apache 2. Then we've got the ignore list, so similarly uninteresting. One thing, like if there's effectively some caching and some tooling that's being downloaded as part of the image build process that's gonna stay around, so we want to ignore those. The image itself ends up being os-image something something, so we ignore those. And then the secure boot files are also gonna be stored there, and we're gonna ignore those as well. The way I see it happening for Incus OS itself, as far as distribution in the future, is effectively gonna be with we'll probably have like a GitHub actions, effectively dump the secure boot certificate as a GitHub action secret, so we can have a GitHub action that generates the image every day and signs it. For environments where you want something a bit safer than trusting GitHub actions, you can obviously do your own builds with your own key. You'll see later it's actually very easy to build one of those images once all of the right files are where they're supposed to be. So next step is the actual initial image. So that's got quite a few files. We're gonna kind of go through that. The main entry point is just saying this is makeOSI setup. So that just says, and there's just one config that basically says we need a tools tree. So that's that Debian tools folder. So just set that up. Then we've got a bunch of files to kind of define the rest. The first thing is the base distro. So we can say we're building Debian testing on Intel with the default Debian mirror, and we're building with non-free firmware installed because we need firmware. We're trying to keep things small, so get rid of all the documentation and the recommends. Then there is the output. So what do we actually expect as an output file? So say like we want to call it OS image. We want it to be a disk. So that gets us a raw disk image. And then the validation stage. So we want secure boot enabled, and we want everything to be TPM measured and signed. So that's the PCR part here. Then there's the kernel. So for the kernel, we need a couple of packages installed, so kmod and systemd boot. This then runs a script that we'll see just below. The image is bootable. We want it to be as a unified kernel image with the kernel modules in the initRD. So we've got proper support, like for most common hardware. Then the kernel command line here is configured to log to the the standard serial console. That's particularly useful when testing under Incus. We'll probably change that for an actual production build. There's a way to actually make all of those files kind of dependent on, I don't remember if they are tags or what, but effectively say only include this piece if, and that will make it possible to effectively have us have multiple targets for like, this is a production build or this is a debugging build. And then if it's a debugging build, we can put those different config keys in place and kernel boot parameters in place. So we can have an environment that's easier to debug. Okay, next up is the kernel install. So it's actually pulling the kernel from my own repository. So see we're pulling it from the stable repo using the Debian 12 package. So just installs the kernel. Then a bit more config. So effectively just says time zone is UTC, local is just C. So effectively default strings in UTF-8 for everything. And we don't want a root password at all. Then you've got some basic packages that are needed mostly so that the system actually boots correctly. So that's dbus. Actually, proc ps is not strictly required. I should remove that and put it into more of a debugging thing. That's mostly because I like being able to list the processes that are running, and without proc ps, it's a bit of a pain. But I should actually remove that. Then we've got dbus, systemd, ZRAM. So that's the compressed swap feature. TPM2 tools, which is required by systemd to do all of the disk encryption bits, and udev, so we can actually detect additional devices and all that stuff. After that, we, as mentioned, disable shells. So there's no SSH installed to begin with, so I don't need to care about that. But we turn off the systemd TTY, like the text console generators completely. So there is no shell running on the system. Do some more cleanup, and this thing is going to get expanded probably a bit. I'm just trying to keep the image to bare minimal size. And the reality is this is never going to be used by an actual, like, we don't expect a normal user to get a shell on that system. So effectively anything that's not needed by the system can be removed, and that just shrinks the image more and more and more. So once we get the full package selection we need on the base OS, we're going to probably be extending that list a fair bit to effectively remove anything we don't actually need from the system. And this is usually a terrible idea to do that on any Linux system, because then package updates and everything are all kind of wonky, but this thing will never be updated. The only way you update this is by building a new image and rebooting onto it. To that effect, it even doesn't have apt. Like, it does have the package because it needs that to actually install the packages, but the apt package manager actually gets removed. Then we've got a bit of extra data here for the partitioning. So effectively that says we want a root partition ext4. It needs to be at least 1 gig, and want it encrypted with a TPM. So it will take whatever space there is left effectively and turn that into a root partition that's encrypted. Then we've got some stuff I took from Incus. So that's the debugging shell. Effectively, that's the Incus agent loader that's copied into there with its systemd unit and the udev rule to start everything. So that's just so I can actually get a shell. Then we've got the rest of the partitions. So the first one here, ESP. So that's the EFI system partition. That's where the kernel, the unified kernel image is actually stored. We might need to bump that size because we need to store at least 2 for AB. And I think because we need to put the kernel and all of the initrd and all the modules and all that stuff in there, we're getting close to 300 megs. So 2 will fit, but we don't want to have an issue down the line where it keeps growing and it won't fit. So we might need to bump that to 2 gigs just to be safe. The user partition, so it's using EROFS, so it's a read-only file system. It stores the files for the /user tree. It is verified, so we can see Verity here being configured and set up to compress and be as tiny as possible. Then we've got the Verity tree itself, which is its own partition. And then lastly, we've got the Verity signature, which is then tied to the secure boot tree to make sure that everything is signed from start to finish. And that's pretty much it for the actual files that define the image. So as you can see, there's currently no system extension in there. There's no Incus being installed in there. It's really just building a tiny Debian testing-based system and stripping it as much as we can, and then turning that into a signed image that you can boot. Next, we've got, I believe, the makefile, right? Yeah, makefile. So we currently have two targets effectively, well, three. One is just a basic clean target, cleans everything up. Second one builds the image itself, and that is to run as root because we mess with partitions and stuff. And then the third one is a test command which actually uses Incus. It converts the raw disk image into QCAR2. It adds some metadata, imports it as an image inside of Incus, and then creates a new VM with, so it turns off secure boot because we don't want the Microsoft keys in there. Then for CPU, 8 gigs of RAM, so I've got plenty of resources. Adds a TPM, and then starts the thing. And what happens then is that because secure boot is not enforced at that point, it will be able to load its own key and then boot the system with the new trust, like the new secure boot root of trust being in place. And the last commit is just the metadata tarball, which is probably just binary data, so not useful. Yeah, there you go. So it's just the metadata tarball that's used for the test image. All right, so let's see, a terminal. Okay, so this is exactly the same stuff I've got on GitHub. So that's just, whoops, except I've got the Debian tools and stuff in place. Okay, let's just look at this thing. So if we, yeah, it's effectively the same stuff, but I've got an image already in there. I can actually do a cleanup of everything. Oops. Okay, so that's good to know. I clearly never ran clean before, so that shows that the RM should also run under sudo, because this is also created as root. Okay. There we go. Okay, so that should be significantly cleaner. Yeah, we just have, I suspect I still have the keys. Yeah. So make OSI, cert, DAR key, all that stuff is still there. I don't actually remember. I think we're missing another step in the make file for those to generate them. So let's just remove them and then do make OSI. What's the commands? Gen key, I think, isn't it? Yeah, gen key. Okay, so if I do gen key, what does it get us? It gets us all, well, CRT and key, so that's good. Key would expire 730 days. Okay, so that may or may not be an issue for you. We're probably gonna do like a much longer expiry on what we use in production, but for testing, that's perfectly fine. What happens if I run it again? Already exists, okay. And fails, okay. So, because what I effectively want to do, and I don't remember if make files in, what's the syntax in a make file to make it ignore a failure? Is it make file? Yeah, it's just a dash. Okay, that's what I thought it was. Okay, so we can do in the build, so do the cleanup and then just do make OSI gen key. So if we run that, it should generate what should fail because it's already there, so that's fine. And then if we do the minus in front, then it works. Cool. Okay, so we're just gonna. Oh yeah, and also I added the manifest. Sure, I need to comment that too. So let's just do that. Make file. Fix cleanup as non-root. So just do that one, and then make file. Generate secure boot keys if missing. It's just that, and then manifest. Okay, so just clean that up and just push it, it's fine. There we go. Now, and I don't think we want clean to delete the secure boot stuff. That would actually be a bit of a problem. Oops, I should not have done that. Okay, cool. So that should be all cleaned up now, and we can do an initial build. So what that does is it generates a secure boot key, and now it's gonna go and build that Debian tools tree. So effectively what's going on is to have this stuff run the same way pretty much everywhere. Make OSI doesn't really want to use the tools like systemd and all that kind of stuff from your current system. So instead it builds itself a small, in this case, Debian-based tree that includes the expected version of systemd and systemd tools and all that stuff. And then it uses that environment to build the rest of the image. It's effectively reusable. That's why that directory sticks around. And there's also a package cache that's also written as part of this to make things go faster. Like for me, rebuilding the whole image from scratch, when I don't need to also rebuild all of the tools in the cache, takes about 2 minutes. So that's still pretty quick. It's gonna get worse once I add things like ZFS, because ZFS needs to compile a pretty big kernel module. And well, that's always a bit unpleasant, and it's gonna take probably a few more minutes. But you know, so long as we can build an image realistically in less than 10-15 minutes, it's still gonna be very good for what we need. Mostly because a bunch of people are just gonna use whatever is generated on GitHub, and for those who do build their own image, they're not gonna do it, you know, every 5 minutes anyways. So this works out pretty well. So yeah, we're now building the actual image. So we're in the kernel stage. So it's pulling from my kernel package repo here, and is effectively getting all of the list of modules and all that stuff that's needed for the init RAM disk. Okay. And okay, the init RAM disk should be fine. So it's effectively now setting up the rest of the system, and then we'll have an image. Right. So anyway, make OSI is pretty convenient. Like it's effectively a reasonably small piece of Python. It's nothing super fancy. That's developed by a bunch of systemd related folks, and it's particularly useful because it does know how to handle all of that secure boot, TPM, read-only OS, DM Verity, multiple layer, sysupdate, all that kind of stuff effectively for you. So you just need to dump a bunch of INI type config files in a bunch of in your tree, and then run the tool and just builds everything. Like once I do put in place the sysx layer, you're effectively gonna have to reshuffle the tree a bit to have multiple images. So there will be a base image, like a base image, and then next to it an additional Incus image, which depends on the base image and just stores the delta. It effectively does that for us. I see that Jared is asking whether makeOSI could be used to replace distro builder, and that was brought up before. I think actually by some of the makeOSI guys or someone who was using makeOSI quite extensively, and it might be possible to use as an alternative to distro builder in some cases. I mean, clearly this is building an image that Incus can consume, so yes. But the main goal of distro builder is to build an image in like that is supportable by the distro that we're building. This stuff is not like if this was like a writable OS image and you were installing that and running it, and you went to the Debian folks to get support on that, they would be like, what the hell is going on with this system? We can't support that. Because the initrd is generated more like the Red Hat way, instead of using initramfs tools on Debian. The bootloader and UKI stuff is not what the distro does by default either. It's being built by tools that are from outside the distro. It's like there's a bunch of things that make this tool work really well, like in a very, very reproducible way, which is great. But it's not the preferred ways that distro engineers would want you to do it, and so makes it harder to support in that environment. But if what you're looking at doing is building, an appliance type image for some software you're developing, this is perfectly fine. It's kind of similar to building a Docker image. Docker images kind of do the same kind of trick where they very actively remove OS files and clean things up and do a bunch of stuff that if you are doing that on a normal standalone writable Linux system would get you into trouble because you won't be able to apply normal updates anymore. You'll have massive issues when you dist upgrade, all that kind of stuff. But it's perfectly fine because it's just a container image and you'll never actually do an update on it. You're just going to throw it away and use another one. And it's much the same thing here with those OS images, and that like they're designed to be as lightweight as possible, to work exactly the way we want them, and to be easy to rebuild, but not be like not necessarily follow distro guidelines and not be something you could run, for the next 5 years doing package updates on and doing that kind of stuff on. Anyway, we've got an image. So if we look at the files, now we have a few more things. So we've got OSI image EFI, that's the UKI. So we can actually see that I will definitely need to increase that partition size because as it stands, we already can't fit 2 of them. That's because literally every single kernel module was stored in the initRD. There may be a way to trim that down in the future to, we don't need every single kernel module in there. We can have a bunch of those that go on the disk partition instead. We only need everything we need for boot. So you need most of the network stuff, most of the storage stuff be in there. So there's probably some way to kind of lighten that and make it much smaller on the EFI side. At the same time, it might also be that it just doesn't really matter, and that just having everything in there doesn't really add any significant delay or issue, and we just make the EFI partition bigger and we're good. And then the full raw disk image is 1.7 gigs, but as it shows, it's actually 1.7 gig, but consumes 575 megs. So pretty much everything is in there. There's effectively close to nothing left on the system itself. All right, now for testing, you can just run make test. So I already have an instance here and an image here, so it's deleting that for me. And then it's converting to QCar2, it's going to be importing that into Incus, and then create the VM and get us the text console as it boots. So here we go. It's going to show some errors because it's the first time that secure boot key is used, so it's actually getting it loaded into the firmware. So that's fine, and now it's actually doing the reading of the massive 500 plus megs EFI image, so that's effectively getting loaded into memory. And there we go. We're now into the kernel, and the kernel is going to look at the initRD and then boot the system. There we go. And next step is going to be, we're going to see it take a bit of time repartitioning. So that's what it's doing right now. It's generating the partition and doing the TPM signing stuff. And we're done. So at this point, like, it's not necessarily visible that we're done booting, but we are. There's no login prompt. There's not going to be a login prompt. And you can't get anything by hitting enter or anything, but we're done. The system is fully booted. What we can do is get another shell. And as mentioned, we do have an Incus agent running in there. So we can do, was it like test Incus OS, what it's called? Yeah. And get a shell. Now, as mentioned, I did install PS so we can see what it's running, and that's what's running. So basically nothing. We've got systemd itself, journald for logging, udevd for the events, networkd for the networking, dbus daemon is running for communication with systemd, and login because I just logged in as a user. And that's it. The system booted correctly, so there's no error or anything. All the services are fine. But this is what the system looks like. And yeah, if we look at the partitions, We can see there's a dev mapper device, so that's actually an encrypted, that's the TPM encrypted root. We can see it expanded to 18 gigs mounted on Slash. And then you've got the user partition, so 669 megs mounted on Slash user. This is compressed and no available space, but it's also fully read-only and measured anyway, so it's not like you could write anything, even if, like there's no need for spare space there. Then dev is a tempfs, so we've got a bunch of tempfs kind of all over the place, managed by systemd. It's fine. And that's basically it. I mean, the Incus agent is running as mentioned, and the EFI partition is available. So we can take a quick look at that and see what's kind of stored. Oops, no, let's see, EFI there. So we can see we've got the kernel itself is there, and then the kernel config and the config files for systemd boot are all kind of there. So that's systemd boot itself is in here. We can see this is the UKI, so that's the super large EFI binary that we generated. That's another copy of systemd boot so that the system just picks it up automatically. And then we've got some configuration on the on systemd boot itself. So it's got the support here for automatically enrolling the keys, the secure boot keys. So that's what we saw happen on the first boot. It's got its list here of just what's that one? No. It should have the boot entries. Actually, it doesn't even need to. I guess it's just picking up. It's just scanning and picking up the right thing automatically. It looks like. It does have some credentials. I'm not actually sure what's in there. Like it's that's probably the disk credential. That's the PCR logged value, something like that. So anyway, that stuff is effectively all generated for us, managed for us, which is nice and convenient because that's where things can get a bit tricky sometimes. And yeah, the system just works. We could try and just reboot it to see what happens on second boot, which, yeah, the reboot command doesn't exist, so we need to do a system kind of reboot. There we go. Dev IncusOS. Oops, test IncusOS. Just hope I didn't miss the boot. I might actually just do another restart after, just to catch it. Because I think we're already at the stage where it's reading through the massive EFI file right now. Since it's taking a while. Yeah, that's where we're at. So that's just gonna be booting. Okay. Second time to charm. Third time to charm. Okay, come on, Incus agent. Let's actually show why we're hitting that code path again. That's interesting. I did reshuffle some of that stuff recently, so it looks like we have a problem where it doesn't correctly detect that it already did the... oh yeah, it failed. There we go. Failed to set up crypto on the root disk, which then got it to try and recreate the root disk, which obviously wouldn't work. So we're stuck. Interesting. Gonna have to debug that one to see what's going on. I don't know that there would have been anything that would change the TPM state. That may be, ironically, maybe the enrollment of the secure boot key did cause that. Initially during development, I wasn't actually running the VM that way. I had a persistent VM where I had loaded the secure boot certificate in to avoid that. Anyway, that also shows another thing, which is that we do need a fallback mechanism. So one thing we'll need to expose actually through the Incus OS daemon is the ability to generate recovery keys, so that you can generate a key for well, any kind of issue with the TPM encryption and just provide that instead. That's again very similar to what Windows and other platforms do, but that will take care of this in this case. The other problem here is that I can't actually, I don't believe I can get a working shell because we don't have a shell. So it shows that cannot open access console root account is locked. So that's fine. I mean, again, like it's a very locked down environment. When I actually do debug, I do set a password and can bypass that kind of stuff to go look at what's going on. But that's effectively an early look at what I've pushed on GitHub so far for Incus OS. Like I've got some initial code on the side for the management daemon, for the APIs. I've got some stuff that's almost work on the sysupdate side, so I need to push that. And yeah, you'll probably see things actually starting to getting upstream and pushed into that repo over the next few weeks, up until the point where we do get something that's fully functional. I'm hoping that like I'm doing a bunch of travel in September, so it's going to be a bit tricky to get too much upstream at that point. But hopefully by towards the end of September, we'll have something that's actually builds daily images on GitHub that people can start playing with. And also a bit more documentation and targets and stuff for like how do you build a production image, debug image. We might actually have GitHub Actions build multiple different versions so that you have the super lockdown production one, but you also have one that's more debug friendly, where you do have the ability to get a shell, you do have the Incus agent running, that kind of stuff. And just make sure they're signed by different keys so that if like on the production system, once you've loaded the production key, you won't be able to just have someone, trick you into switching to the version that's not locked down. All right. Let's see. Let me just look at the question real quick here. Google is always a bit annoying by putting emojis and stuff on top of the chat window, which makes it hard to read. If I pop it out, that usually helps. Let's try that. I'm not sure what you mean, Jared. You're like, since we're not using Windows, is there any other methods we can use? What do you mean? Like, effectively nothing in there really depends on Windows. Like it does, like we do things in much the same way for the TPM encryption as what BitLocker does, but there's nothing in there that that's really Windows related. The one thing that I guess that might be is that the default state of Secure Boot is to have a trust key that comes from Microsoft, which is used to sign everyone's bootloaders, not just Windows's, but also the one from. This is how Windows does it. I mean, that's for the. So the question was again kind of about the TPM encryption and BitLocker, and I mean, yes, that's how Windows does it, and that's how Linux also does it, because it's the way that tends to make sense. Like effectively, you want to measure the bits that could be problematic if they changed. So that's things like firmware, kernel boot parameters, the kernel itself. So effectively anything where if it changed, it might make it possible to steal your data. So you want to have that measured and then use and then lock a key tied to those specific measurements, and then be able to pull that key and decrypt. In all cases, you kind of need to have a fallback mechanism, because otherwise someone might accidentally reset their TPM or change something in the firmware and no longer have the right state. So some recovery mechanism is required. And for that, on Linux, the two common ways are either straight up prompt for passphrase. So that's what, if you've done full disk encryption on Linux, most likely you're familiar with that. At boot, it's like, please enter passphrase for disk XYZ. You enter that passphrase, that unlocks it. And a LUX volume, so like an encrypted volume on Linux, has multiple slots for its key. So it can have the TPM key for the current version of the OS, the TPM key for the expected state of the new version of the OS, and then a fallback key, which is either like a passphrase, but could also be a file on disk that's being read. So if it's a file, that's where you can put like a USB stick or something like that as your recovery key, effectively. So that's how that stuff usually works. And yeah, the mechanism normally works pretty well, because the older way of doing this on Linux was with just a passphrase. But when you're managing a fleet of servers, that becomes quite annoying, especially when they're remote and when you might have like your VPN server running on that server for some reason or anything like that. Like you don't want there to be, an unexpected power cut, all of your machine restarting, and you having no way whatsoever to connect to that console to enter the passphrase. So that's where tying the encryption to non-good TPM state allows those machines to just immediately boot back. And yeah, ironically, that's also, I mean, we saw a good example of that with the CrowdStrike thing, where because the OS effectively got corrupted in some interesting ways, the machines would then have to enter the passphrase to unblock, which I guess on servers wasn't all that terrible, assuming that there was a proper recovery key set up that people could access, that people could enter. You could do it reasonably easily centrally. The main issue of the CrowdStrike thing was that CrowdStrike was mostly run on end-user devices. So that meant like corporate laptops with, a lot of people having corporate laptops where they don't have that recovery key themselves. The recovery key is effectively managed by the organization, so then they needed to either have someone give them the recovery key or show up in person for someone to enter the recovery key, boot back into Windows, fix things. Like that was a whole mess. In this case, I don't expect that to really be a problem for us because we will effectively have like at least 3 slots used with like current OS expected state, next OS expected state. So those are the automatic TPM based keys. And then a recovery key after that, which is most likely a passphrase. And you'll actually be able to create more of them if you want to. Like I don't remember the slot limit on Lux, but there's more than 3. So you'd be able to have other additional passphrases if you wanted to, that you could give to staff or whatever. Makes sense. All right. Yeah, so I was kind of hoping to get to, add ZFS or add some more significant changes to this, but kind of running out of time. So gonna have to leave it here for this one. But hopefully that was a good initial look at kind of how that stuff works, all of the different make OSI files to build an image like this. And you're gonna see more changes kind of floating into that repo over the next few days to both grow the initial base image to include all of the things we need, add the sysx layer for it to actually have Incus in there, fix a bunch of issues, like I said, like we need to grow the EFI partition so it can actually fit 2 images. Need to sort out whatever happened with that root partition on reboot. Or at least have a way to immediately put a backup key and see if that was the problem. And put the sysupdates logic in place. We've got AB with a way to actually provide a replacement update, like a replacement image to fill the other slot. Then put in the management daemon and wire it up through Incus. Put in some of the initial provisioning logic, so you can just provide those networks, that network config in. And at that point, we should be in pretty good shape. Like there's gonna be more work needed on the daemon side, specifically to handle things like properly installing, pulling updates, all that kind of stuff. But once we do get a working base image that we can reliably automatically build on GitHub, that can be properly signed and that has a way to getting updated, even if it's manual at the beginning, then we're effectively at a stage where it's going to be much easier to iterate on this because people can start running that in the test VM, can pull updates from the dailies and just help out with building this thing. Again, just to clarify, like we would still very much care about the other ways of installing Incus. We just think that having all 3 ways makes a lot of sense. So regular packages on top of normal distros, that's what most people run on their laptops, even on their home servers and the like. Having Incus deploy that's used to deploy at larger scale clusters using Ansible, again on normal Linux distros. And then the third option, which is this, with like something that's much closer to a VMware ESXi image or like a Proxmox type image, where it's the whole package as an appliance that you can just put on a machine, boot up, start using, and you're done. So pretty excited future. Very good to see that we're like making good progress on kind of all three fronts. Like on the normal packaging front, I've been helping out with some of the Rocky Linux guys over the past few days to getting the enterprise Linux package working better. So we're getting there. It's not in EPL yet, but we're getting there. On Incus deploy, we've got it doing LVM cluster and a bunch of other things on Ubuntu and kind of initial support for Debian, and we'll look at adding other distros there. And then Incus OS, with initial code dump happening now, and more logic that's going to be added over the next few days and weeks. So there you go. Thanks a lot for watching this. I realized this was a lot more of a talking heads type thing than usual. But I think it was useful to providing a lot of the kind of context on how this stuff works, what are the main goals, all of the security aspects, and kind of where we're going with it. And then I'll probably have some future live streams showing more changes going into Incus OS and kind of where it's headed. Again, thanks a lot for watching. Thanks a lot for your great questions in chat, and see you next week for another video. All right, have a good one. Again, you can leave your questions down below or on the forum as usual. Thanks a lot. Bye.